All right, good morning, everyone. Welcome back to Math 161. So we've got our due dates of everything coming up, including from today to the next week. 2.5 due today, 2.6 next classes day. Of course, everything's due by midnight. And then 2.7, which we'll finish in class today, will be due on the 30th. We will cover pretty much everything in 2.8 as well. So we're going to finish that last roughly half of 2.7, and then we're going to finish about 90% of 2.8. So we will still have one example, well, a part A and part B. So one example to do next class. However, we will have done enough for me to say that the section has concluded, which is why our test 2 is going to be in a week. And that's the same details as last time. Specifically, this will be on sections 2.1 through 2.8. So when I say same details as last time, I mean there will be a review in my math lab. I'm sorry, there will be a review in Canvas for you to check out with questions and answers. The test will be in my math lab under the quiz and test section. It will only be available those 2 days. You still have to take pictures of your work or scan your work and submit it in Canvas. There will be a spot for that. Everything has to be submitted within 15 minutes or I reserve the right to give you a 0. Any kind of partial credit request you have, you need to email me, specify question numbers and everything, and then I can do that for you. So if you don't know any of those details for a test, you can shoot me a message in chat or an email later, but I don't want to waste any time. I'm about a minute, I started a minute later than I needed to, so let's go ahead and pick up where we left off in 2.7.
All right, welcome back, everyone. Remember, we are in 2.7. We're, I don't know, I don't want to say halfway through 2.7, maybe a third of the way through 2.7. I am going to try and finish this section as well as 2.8 today. I would really, really love it if I can make our test a week from today, which would be Wednesday and Thursday of, what's that, November 3rd and 4th, 4th and 5th, 4th and 5th, 4th and 5th, as we previously discussed. So I'm going to go ahead and get right into it. As I said, if I get to the very end of 2.8, but we haven't finished maybe 1 or 2 examples, I will still hold that test a week from today, because the last bit of 2.8, it's literally just 3 formulas, plugging numbers into formulas and simplifying things, just memorizing the formulas. So I won't feel awful if I have to give you, one last formula a class before the test on it, because again, it's just a formula, it's cookie cutter. But let's not waste any more time. We talked about the idea of inverse functions last class, and that they're kind of like opposites of each other in the way that addition and subtraction, we think of them as opposites. In the way of multiplication and division, we think of them as opposites. Opposite's not really the right word in that last case, but it's, we think of that as opposites. So it's more known as reciprocals with multiplication and division, but some people go ahead and give them the true word, that is inverses. So addition and subtraction are inverses, multiplication and division are inverses. It's all about, if you do one thing and then the other thing, they cancel each other out. That's the idea of an inverse function. So if you compose a function in a function one way, it'll cancel each other out and you just get x. Or if you compose the functions the opposite order way, they cancel each other out. This f of g is basically like doing f plus g, and then, I'm sorry, f, hold on, let me just give regular numbers. It's like doing 3 plus 3 and then minus 3. I said 3 too many times. 3 minus 3. You have a positive 3 and a negative 3 and they cancel. Or a 3 divided by 3 and they cancel. Or a square root of 3 squared and the square root and square cancel. So this stuff, when you do an f of g, if they're inverses, it's like they cancel, but the answer is x. Now, under addition and subtraction, we say the answer is 0 when they cancel. Under multiplication and division, we say that the answer is 1 when they cancel. So for this inverse function concept, when they cancel, you get x, which is your input variable. Well, we said that you have to do the composition both ways in order to say that 2 functions are actually inverses. And not only do you have to do the compositions both ways, they both have to equal that very specific x. So even if you do the composition one way, if it's not x, then you go ahead and stop. But just because you get x for one of them does not mean that the second version has to be x as well. We also talked about how inverse functions, the idea is you're just swapping x's and y's, whether they are the literal variables or they're the coordinate pairs or the graph, and then that's still coordinate pairs. We talked about what it means for a function to be one-to-one. We'll get into that graphically a little bit later. But then finally, we gave the instructions on how to, instead of be given two functions and say whether they're inverses of each other, in other words, whether they cancel each other out by putting one inside of the other, this is when we just start with one function. So we only give you one function, and we know that it fits the parameters to be invertible. To be invertible means you can find an inverse. So those steps were change your f of x to a y, and that's just to make things a little simpler in the next couple steps. Then you swap the x's and y's, which means anywhere you saw an x, you rewrite it as y. Anywhere you saw a y, you rewrite it as x. Then you'll have a brand new equation that you'll solve for y. And then once you do that, you're basically done, but you have to use this notation, this f inverse of x, you have to replace it with y. Now, I love a good handwritten test for this because so many students forget to write that notation, and then mean old Mr. Evil gets to take away a point or two for you not understanding the concept. Unfortunately, my math lab always just writes this for you. But you need to understand moving forward, just because my math lab does something convenient for you in here, doesn't mean it's going to do it for you later. You have to understand the concepts. So when you write it as y, you are not demonstrating that you know it's an inverse function. When you write it like that, you are demonstrating that you know it's an inverse function. And then we just mentioned that in that previous example we did, the very first one, not the second one, that because they were inverses, we could have said that f was g inverse, or we could say g is f inverse, because of that two sides of a coin argument. And with that being said, I have got something on my drawing tablet and it's catching. It's weird. So example 2, we're going to find f inverse of x given that f of x is 1-1, which means 1, 2, 1. Not the number 2, the word 2. T-O, not T-O-O. So we're going to give you a function. I'm telling you it's 1-to-1, so you don't have to prove that, because if I don't tell you, technically you need to prove it, and that can be complicated depending on the problem. We're going to start out with a problem, with a function that should feel very familiar if you just took the last notes today. 5 days ago, maybe it won't feel that familiar. Excuse me, 2 days ago. But in case you don't recognize it, it's the same thing as f of x from example 1a. Now guess what? Back in example 1a, we proved that these two things were inverses of each other, which means this is what our answer should be. This, x minus 5 over 2, is what our answer should be. We already know it. We usually don't know it ahead of time, but this time we do, because I wanted you to be able to compare and contrast. So let's follow these 4 steps explicitly. I'm going to back out just a little bit so I can keep them on the screen. So here's what we do. First, rewrite f of x as y. So I'm going to use color to show the change. Rewrite f of x as y. The reason we do this is for convenience, because the next step is we swap the inputs and the outputs. The entire idea of an inverse is inputs and outputs are swapped. X's are inputs, Y's are outputs. Now f of x is still the output, but it would just look really weird if you made this x an f of x. All right, so here's me swapping. I'm going to change color again. So now this y becomes an x, and then this x becomes a y. Everything else stays. The equals, the 2 times the y, and the plus 5 stay. 2 is just a little skewed. There we go. Skewed, not screwed. Again, the reason we chose to write this as y is because if we didn't, this would look like 2 times f of x, and people really start getting confused with that. They'll start thinking that x means a times again, and that's definitely not the case. It's just notation. So someone could certainly get this thing right by making that f of x, but trust me, you're going to have a harder time. And then finally, we solve this equation for y. That's a pretty common thing that we like to do, is solve equations for y. Now, at this point, this could be simple, or it could be a little more ugly. Spoilers, this one's simple. Not even going to write out the steps. We got to move the plus 5, so we're going to subtract it on both sides. So that's going to give us x minus 5 is equal to 2. And then to y, x minus 5, again, the plus 5, I subtracted 5 on both sides. So that's now an x minus 5 on the left. There's no more 5 on the right. And to get rid of a 2y, we're going to divide both sides by 2 so that they cancel. Again, these 2's are the things that cancel. So then that gives us, wow, I need way more room than what I thought. It's okay. X minus 5 over 2 is equal to y. Now, if you stop here, that is wrong, because you are not demonstrating that you have just found an inverse, which is why that last step says write f inverse instead of y. So we just changed the y to an f inverse. So x minus 5 all over 2 equals f inverse of x. Yes, you can certainly split this as x over 2 minus 5 over 2 equals f inverse. But the reason I chose to write it this way is because, well, that's how the answer to 1a looked. Or not the answer, g of x. So f inverse is g of x, as we said earlier. We did not lie to you. B, f of x is equal to x cubed plus 7. Let's step it up a notch. So this is, when you go through this algebra, if you do this 10 or 15 or 30 times, like you really should to learn something, you start recognizing why one function has pluses and times and the other has minuses and divided by. Because when you swap the x's and y's, solve for y's, you end up unraveling the things you had to begin with. So if you had a plus, it becomes a minus. If you had a times, it becomes a divided by. But it can be very difficult to predict how everything should look, especially as the f of x is more complicated. So again, as someone who's done 30 of these, with the f of x having a cubed and a plus 7, I predict that my inverse function would have a minus 7, and what's the opposite of a cubed? Not cubing again, it would be a cube root, because we'll have to get rid of that cubed eventually, and you'll take a cube root to do so. So I expect that the inverse function is going to have a minus 7 and a cube root somewhere, but I can't necessarily predict exactly how it's going to look. So even I have to do this process. So first step was to write f of x as y. So y equals x cubed plus 7, going back to old school notation. Second step, swap the x's and the y's. All y's become x's, all x's become y's. Everything else stays. See, I don't give the 3 to the x on the left here. Now it's with that y. You're literally just swapping the variables, no other components. And then your third step going to solve for y. So we will subtract 7 on both sides. I'm not going to show that algebra there. You get x minus 7 equals y cubed. But I will show this step. If you have x minus 7 equals y cubed, to undo a cube root, to undo a cube, you cube root both sides. And you don't need a plus or minus since it's an odd index. Again, if this had been an even power, you'd need a plus or minus, maybe. Now that's normally the case, but I'm going to get there, and there's some special cases involved here. But let's not talk about too much at once. So the cube root of x minus 7, nothing happens there. The cube root and the cube cancel, so you just get a y. If you stop, nope, that's wrong, because you did not acknowledge that that's an inverse function. So you change y to f inverse. So we get the cube root of x minus 7 is equal to f inverse of x. And there really isn't a way to rewrite that, so that's the only version of the answer. So now what you could do is, if I gave you another example and I said, if you have f of x equals x cubed plus 7 and g of x equals cube root of x minus 7, and I asked you to prove that they're inverses, sure, you could do the composition both ways, but you could also say, well, hey, if I start with one and I do this process, I can get the other, which is exactly what I said g of x is. Boom, they're inverses. So this is an alternative method to have done example 1. You don't necessarily have to do these compositions as long as you're good with the mechanics. You can just start with the f of x, find its inverse, and if it matches g of x, then they're inverses. You could also start with the g of x, find its inverse, and if it matched f of x, then you know they're inverses, otherwise they're not. So there are 2 ways to have done example 1, and now we know that. All right, let's do more of these. C. This is one of my favorites, and it's one of my favorites because of the answer, and we'll get there in a few minutes. So f of x equals 1 over x. First step, let's pull back. Write f of x as y. So we get y equals 1 over x. Second step, swap the x's and the y's. So any y becomes an x, and then any x becomes a y. So that's in the bottom. X equals 1 over y. Third step, solve for y. Oh no, the y is in the bottom. What do we do? I've never seen this before. Don't you dare say that. You've definitely seen this before. This is a fraction equation, and I gave you instructions on how to get rid of fractions in equations. You multiply by the LCD. The LCD, in this case, is literally the only denominator we see, which is a y. So we have an LCD of y. So we're going to multiply both sides by y. We multiply both sides by the entire LCD. Every term by the entire LCD. Not top and bottom, just top. Because then that would get the y out of the denominator, and you got no more fractions, which makes this a lot easier to understand. So now we have x, y equals 1. You could have written the y first still, that won't matter. Now again, we're trying to solve for this y, which means since it's multiplying by x, we need to divide it. Divide both sides by x. So that those x's cancel, and we now have the y isolated, giving us y equals 1 over x, but then the last step says to write it as f inverse. So we get f inverse of x is equal to 1 over x, and that is our answer. Now you might be thinking, oh, Mr. Beckner likes this one because the f inverse ended up on the left. That's completely arbitrary. When we had the f inverse on the right of these, you can just swap them if you want them to look more normal. That's the same. So don't think that was the reason. The reason I thought this was fascinating is, go back one more, look at the original function, look at the inverse function. What do you notice? That's right, they're the exact same thing. No one, I don't think, would have ever predicted in this course right now that the inverse of 1 over x was itself. How is the inverse of a function itself? Well, let's think back to just addition, subtraction, multiplication, division. Remember, when we talk about addition and subtraction being opposites, a fancier word is now inverses. So think about trying to find a number that you could add or subtract to itself and it doesn't change. 0. 0 is its own inverse because 0 and negative, positive and negative 0 are literally the same thing. All right, well, what about multiplication and division? What number divided by itself or multiplied by itself gives you the same thing? 1. So 1 is its own inverse under multiplication or division, because if you multiply by 1, you get the same thing. If you divide by 1, you get the same thing. So there can be functions, and this is not the only function, in fact, that is its own inverse. There are many classes of functions that can be their own inverses, but we're not going to get into all that jazz. But again, I think that's fascinating because this is a really complicated function. And we've been dealing with these rationals a little bit here and there. We've definitely done some algebra with them. We've talked about their domains. But what we're going to start doing in Chapter 3 is graphing them. And that is going to be more complicated than any of the other graphing we do in this course. But what's interesting is the graph of 1 over x, if you did this reflection thing I'll teach you in a little bit, it would look exactly the same as its inverse, 1 over x. It would reflect into itself. All right, don't focus on that other stuff too much. I'm just giving you some deeper thoughts to consider later. All right, let's keep doing some of these. Why did I write E? You know E does not come next. It's D. Gotta go back to Sesame Street, don't I? All right, so let's do another one that's got that over X component, but let's put some more jazz in there. So we'll have some nice dissonant chords. Sorry. Music theory. So f of x equals 3 over x plus 5. So this is different because of the 3 and the 5. The 3 doesn't make it too different, but the plus 5 does make this a little bit more different. A little bit more different. It sounds weird. All right, first step, write f of x as y equals 3 over x plus 5. Second step, write y's as x and x's as y's. Third step, solve for y. All right, so the 3, the 5, they got to go away from the y. But before we play around with that, this y is in the bottom. We don't like that. We don't like the variable we're solving for to be in the bottom. Whenever it happens, the go-to process is to take your LCD and multiply it by everything to clear the fractions. We don't like variables we want to solve for in the bottom. It's very difficult to think about, so we get rid of them. So we say, okay, well, what's our LCD? Well, it would be y. It's the only denominator. So we multiply the x by the y, the 3 over y by the y, and the 5 by the y. You might notice I put the y after the 5 instead of in front of like the others. That does not matter. Multiplication order is arbitrary. I still need more space. Why did we do that? Because those y's cancel and that was the goal. Again, you need to start thinking about the reasons we're doing things, not just arbitrarily doing them. That's not going to help you understand stuff. So you get xy equals 3 plus 5y. And this is the first major complication to these inverse equation solvings, because the variable we have to solve for is in 2 places. And if you're pulling your hair out, we've done this before. We did this back in chapter 1, I think in maybe 1.4. I said with massive inflection in my voice because I don't remember off the top of my head. But when we were solving formulas, when we were solving literal equations at the end of, I think 1.4, maybe 1.5. This was a type of problem we had. So there were instructions we gave back there, and we've been testing on it. And in math courses, you never get to forget things, so hopefully you haven't forgotten them. So remember, the idea here is you want everything, oops, let's get off of the highlighter. You want everything that has a y on one side of the equation, and then you want everything that doesn't have a y on the other side of the equation. Now, the only thing that doesn't have a y is this 3. So sure, you could move everything that has a y to the right. You could move this term to the right by adding, subtracting, whatever. But then you'd have to move the 3 to the left, and that would be 2 steps. That's perfectly fine, but I'm going to do it a different way. I'm going to leave the 3 alone, and I'm just going to move the 5y term over to the left, which means I'm only doing 1 step. So I will write down the algebra this time because it's a little uglier. I'm going to subtract 5y on both sides. Again, not the only way this works. Those are not like terms. Do not try and combine them. But now I've got everything with a y on one side, everything that does not have a y on the other side. Why are we doing this? Well, normally these would be like terms. We'd combine them and then divide by the number in front of it. They're not like terms, so instead what we do is we take a GCF out, which coincidentally is y. There's a y in this term, there's a y in this term, so I can factor it out. And then you're just dividing each term by y, which leaves you with x minus 5, and then that's equal to 3. Again, this algebra right here is not new. If this is throwing you for a loop, go back to chapter 1, again, the end of 1.4, 1.5, one of those two. It was wherever we were doing formulas. It had like the perimeter problems, the volume problems, things like that. All right, so normally this would say something like 7y equals 3, and we would divide both sides by 7. It's just a little uglier, but it's the same algebraic step. This says y times, again, here's our, what I called a 7 before, so we're going to divide both sides by that thing. We're going to divide both sides by the x minus 5, so that we get rid of it, and we're only left with the y. See, those will cancel now, which gives us y equals 3 over x minus 5. And then finally, we write that as f inverse of x. The 3 and the 5 are still there. The plus turned into a minus. The 3 was on the top originally. It's still on the top. Again, it's kind of difficult to predict that. If you do thousands of these, you get to the point where you can start predicting them, but you really do need to show your work for this. don't think you're going to get away without showing your work. So I would say, in terms of the algebra you're responsible for, D is the most complicated. But all things considered, the one we're about to do, E, is, in my opinion, the most complicated. And I don't really want to put it there. I want to just go ahead to the next page for reasons. Let's go with f of x equals x squared plus 11 for x is greater than or equal to 0. Now, before I actually do this problem, I want to point out something. I want to do a completely different problem and then relate it to this one. This is what's new about this problem. I have given you a constraint. I have given you a restriction on the domain. I'm saying that this function, we're going to find its inverse, but only for x values that are positive or 0. In other words, we're not going to allow x to be negative. And the reason for that is, spoilers, if we don't have this, if I did not give you this restriction, this is not one-to-one without that restriction. This is not a one-to-one function. And I'm going to do the algebra to show you why that is. So again, before we do that, before doing E, let's try without the restriction. And let's show you why we have to have that restriction. So I'm going to do this in a, I guess, orange color because different problem. It's not technically E. Let's just do x squared plus 11. I'm going to go through this at the normal, oops, no, process. Write the f of x as y. So that becomes y equals x squared plus 11. Then swap the x and the y. So that becomes x equals y squared plus 11. Then solve for y. Subtract 11 on both sides, you'll get x minus 11 equals y squared. And then whenever you have something squared, and this is where what's interesting is, I would say 8 to 9 out of 10 students, until they've just done this 100 times, they will do this wrong. This is what they'll do. Oh, square roots are square both sides because they cancel. That's wrong. That is not what you're supposed to do in this instance. Whenever you have something squared equal to blah, 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 you are technically supposed to take a plus or minus square root of both sides. Now I say technically because if there's a reason not to, then you don't. And word problems, often there's not a reason to. When we get into trigonometry, sometimes there's not a reason to. And in this case, when we get the restriction, there won't be a reason to, but for now, we'd leave it. We would leave it. So we get plus or minus square root of x minus 11 equals y, and then we switch to the function notation. And we say that f inverse of x is equal to plus or minus the square root of x minus 11. And this right here, this plus or minus, means this is not a function. We talked about that a couple of weeks ago. Because if you just plug in one single number, let's say I plugged in 11. If I plugged in x equals 11, now let me not do 11, let me do 12. That wasn't actually going to show my point. If I plug in x equals 12, then f inverse of 12 is equal to plus or minus the square root of 12 minus 11, which is plus or minus the square root of 1, which is plus or minus 1. That is one input leading to two outputs, which is the literal definition of not being a function. Every input, if you repeat an input, you should get the same output. You can't have one input leading to multiple answers. In the real world, we call that insanity. In math, we call it not being a function. In order to be a function, if I plug in 12, I only expect to get one answer, not two. So this is not a function. So this is the entire reason that I gave you this restriction. This restriction right here says we're only worried about positive x values, which means when we're in the inverse, we don't take a plus or minus square root, we cut out the minus. Sorry if you can hear that truck backing up on my street. So here is the note that goes with that. For this 2e, and it's going to sound a little confusing because remember the domain of a function becomes the range of an inverse function. The range of a function becomes the domain of an inverse function. So by making that restriction, by forcing x to be positive or 0, by forcing it to be non-negative more explicitly, then the inverse function's output can't be negative. Okay, so we're forcing the input of the function to be positive, which means the output of the inverse can't be negative. If we force x to be positive in the regular function, that means the y, or the function's output, can't be negative for the inverse. So again, that same restriction is here. It's just now that the restriction becomes f inverse has to be bigger than or equal to 0. Saying that x is bigger than or equal to 0 in the function means that the inverse has to be bigger than or equal to 0. That is what avoids the plus or minus aspect. So it's interesting because, like I said, 8 to 9 out of 10 students initially don't ever do this plus or minus. They forget it over and 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 over. And eventually I hammer it into their thick skulls that you can't forget it. But again, what's interesting here is a student would actually make a mistake here on f of x on the original function without the restriction because they think to not do the plus or minus, and then they think they'd have an inverse function, which they don't. We will also show this graphically in a, 5 or 10 minutes, but let's actually do the real problem now. So now let's actually do 2e for real, not for play. So we had our f of x, wrong color. Not sure why I hit blue. Oh, I know why, because I was changing it from orange. We had our f of x is equal to x squared plus 11. And we said that x has to be positive or 0, can't be negative. So rewrite f of x as y equals x squared plus 11. The algebra is going to be the same. Then swap your x's and y's. So x equals y squared plus 11. Subtract 11 on both sides. Let me just move over here. So you'll get x minus 11 is equal to y squared. There is going to be no plus or minus here because, again, we said x has to be positive in the regular function, which means now we're in an inverse, so the y has to be positive. So we're not worried about y being negative, so there is no plus or minus. So just a regular old square root of both sides. So the y squared cancels, and you get just a y. And then the square root of x minus 11 is the left side. And that is a function. Write it as f inverse. Boom. This is a very important concept. The original function x squared plus 11 is not a invertible function because while it is a function, while it passes what we call a vertical line test, when you try to invert it with that plus or minus, it would fail the vertical line test as an inverse. So again, the idea that we're going to start talking about is if here's your regular function, then the inverse, it ends up flipping it kind of in this manner. But I can't call that a function because it fails the vertical line test everywhere where x is positive. But by clipping half of this thing, by restricting the x's to be positive so I don't have this leg, what happens is this leg goes away, and now it is a function once you clip it. Where did that go? That was weird. So by cutting one leg of the parabola off, when you do whatever it is you do to create your inverse function, I haven't described it yet, but this is the idea. Now it would pass the vertical line test. That's the idea. We will actually see that as an example in just a little bit, but let's go over how I actually knew to do that. So with graphs, when we're dealing with functions as graphs instead of written out as functions, equations, however you want to call them. It can be determined that a function is invertible if and only if it passes the horizontal line test, i.e. any horizontal line can only touch the graph once. The horizontal line test is the exact same thing as a vertical line test, except with horizontal lines instead of vertical lines. How on earth do you think I knew that? Maybe it's the word horizontal used instead of vertical. Now this is being used on the regular function, not the inverse. See, when we find the inverse, it's only a function if it passes the vertical line test, but this was the graph of a potential f inverse. I'm talking about looking at an original function and without doing all the jazz to find the inverse, just knowing whether you can even do that. So if it passes the horizontal line test, so in other words, if you've got a function that you can draw horizontal lines and every horizontal line touches the graph only once, then it's invertible. So, and you can see, before I clip it, it would have touched twice, but by clipping it, now it only touches once, so that would be invertible. Again, that is going to be an official example coming up. I'm just giving you that ahead of time as an example, a visual example. So finding the inverse of a function given the graph, we're moving on to that for just a few minutes. Let's try this out. We're up to example 3. How am I on time? 35 minutes in, we got a good pace. We're going to do this. We are going to do this. Does an inverse function exist? Okay. I'm going to give you a line. And I'm just going to give you 1 point on it for an arbitrary reason. Here's a point for the line. I'm not going to tell you its slope. I'm just giving you 1 point on the line. And there's our function. So what you do is, first of all, I didn't tell you it's a function, so you could go, well, is it a function? So you draw a bunch of vertical lines, and all of them would only touch once. So yes, it is a function. But that wasn't the question. I said, does an inverse function exist? So spoilers, all three I'm going to give you, they are functions up front. They will pass the vertical line test. So we're more worried about, do they pass the horizontal line test? So you're drawing horizontal, that was terrible. Undo, please and thank you. Horizontal lines, and that would touch once, horizontal line, and that would touch once, horizontal line, and that would touch once. I can't imagine drawing a horizontal line anywhere where it would touch more than once for this. So yes, an inverse function does exist for this. Pretty easy. Easy if you practice. If you're taking a test and you go, oh no, did Mr. Beckner say it can only touch once or it has to touch more than once? If that's what you're going through, that means you haven't put enough time and effort into your studying and practicing. And this is all about time and effort. Laziness will not benefit you. Find motivation. I always love, hey, you do well in school, you're probably going to get a better job. Let me make that a little smaller. And you make more money. So use bread as a motivation if that's what you got to do. These are terrible looking axes. Good grief. Undo. Sorry, I'm frustrated. There we go, a little better. All right, so here is a standard parabola, y equals x squared. Doesn't have to be specifically y equals x squared. It could be y equals 2x squared, y equals 5x squared. But I couldn't have any plus or minus numbers in there because that would shift it, as we know. So does this pass the horizontal line test? Obviously, it passes the vertical line test. It is obviously a function. Any horizontal line drawn down there doesn't touch at all, which is fine. So far, so good. If I draw one on the x-axis, it's only going to touch once right there at that vertex. That's what we call that point, as we will discuss further in chapter 3. So that's okay, and someone will go, yes, it's a function. But they're wrong, because you have to be able to do those horizontal lines anywhere, and if you draw a horizontal line anywhere on the top, once, twice, boom. No, it is not an invertible function. because when you invert a function, left becomes down, right becomes up. So this thing ends up, the inverse ends up looking like this, as we already kind of described, and that would fail the vertical line test. So B here, this B, is literally 2e when I didn't give you the restriction. And you know what? I wasn't supposed to do that at a height of 0. I was supposed to do that at a height of 11. You get the same argument. I just meant to have that as a height of 11. So I'm going to rewrite everything. You don't necessarily have to redraw the example. It's going to be the same conclusion. I just want for my notes for that to be the same example. Third tries the charm, right? So here's a height of 11. Here's our parabola. And here is it failing the horizontal line test miserably. Here it's fine, but anywhere above 11, it fails. So this is literally the graph to 2e and orange ink without the restriction. And hey, it wasn't a function because of the plus or minus aspect here, so when we graph it, it better not, when I said it didn't have an inverse function because the process of finding it gave a plus or minus, which said that was not a function. Same thing here, fails the horizontal line test, so the inverse isn't a function. But what if we clip that in the same way that we did before? So here's our height of 11. And now I'm only going to draw the positive values of this. So this thing is starting at 0. It's not, I've clipped this side off. I don't have the left side anymore. So the convenience there is that horizontal line still works. This horizontal line still works. But now anything over a height of 11 will still work as well. Each horizontal line will now only touch once. So yes, this is a function, as it should be, because we already proved analytically when we cut the restriction, or when we had the restriction, when we cut the negative x values off, it was a function because there was no plus or minus in the inverse. And that was not a B, that was a C. Silly me. So the point of example 2e, as well as 3b versus c, is that you can have a function that wouldn't have an inverse. You can restrict it to a smaller set of x values, and then maybe that will have an inverse function. And when you get to trigonometry, that becomes an important concept because you learn about these sine of x's, cosine of x's, and tangent of x's, and eventually you have to study their inverses. And while sine, cosine, and tangent are functions everywhere, you can go from negative infinity to infinity in your x values. When you try to invert them, that horizontal line test fails infinitely many times. Every horizontal line would clip that function infinitely many times. So you have to restrict the domain of the original sine, cosine, or tangent to an extremely small window, something like 0 to pi or negative pi over 2 to pi over 2. I'm not going to teach you any of that stuff, obviously. I'm just telling you that this will come up again, and you don't get to, that's right, forget it. I am always honest about what comes up again and what doesn't. I am also a broken record. All right, last topic of the section. We're moving at a good pace. I think we're going to get this stuff done today. Finding the inverse function given the graph of f of x. Oh, look, literally the same thing that we did with equations. Swap the x's and y's. Except they won't literally say x and y, they're going to be coordinate pairs, so just swap the coordinate pairs. So in other words, if you had a point 2, 5 for the regular function, the inverse function would be 5, 2. There is nothing complicated about this process. It's just literally swapping numbers. That is it. What you will notice is that the inverse function should end up looking like a reflection of the original function about the line y equals x. Now, some people will do this 100 or 1,000 times, and they learn to actually just reflect it about that line. It can be really difficult to do that for some crazier functions though, so I'm not a huge fan. Me personally, I still just always swap the coordinate pairs. So you can do a reflection, but it's not as easy as just reflecting left or right. It's not it's not like we're just using this as our mirror and reflecting left or right. We're reflecting about this line right here. That's a lot more difficult to do a reflection across because it's not just left to right or up to down. It's left to right and up to down all at once. And man, I don't like doing it. If you figure it out, go for it. But me, I'm going to go with this swapping X and Y coordinates. All right, example 4. Graph F inverse of X. And we're only doing one of these. So what I'm going to do is I'm going to give you the graph, obviously, of the regular function. And I'm going to give you 3 points. I'm going to have a point here, and that point is going to be -1, 0. I'm going to have a point down here. This point is going to be -3, -2. And then I'm going to have a point over here, which I'm going to say is 4, 2. And I could hash mark these off, but this is our original f of x. Now, this middle work that I'm about to show you, a lot of people can skip it and just end up, oh, well, this point's -3, -2, so I need to plot -2, 3, et cetera, et cetera. But I'm meticulous as a teacher, so I like to say you should maybe label these in a system like this. X and Y coordinates were -3, -2, -1, 0, and 4, 2. This is just helpful for some students. This was the regular function. That was our f of x. So to get the inverse function, you just swap the x and the y coordinates. Now I don't swap the x and the y in the table of values because that would confuse you, I think. Sorry if you hear that. Sweeping something off my desk. We're just swapping the pair. So the -3, -2 becomes -2, 3. I didn't just reinvent a wheel. I just changed the order of 2 numbers. 0, -1, 2, 4. So now let's graph the inverse function. So -2, -3 would be left 2 and down 3. So maybe like here. And you could actually, I wrote the numbers backwards. I scaled it appropriately, but -2, -3. So that would be left 2 and down 1, 2, 3. Then the point 0, -1 is left to right 0 and down 1. So there's our 0, -1. And then 2, 4 would be right 2 and up 1, 2, 3, 4. Then connect, connect. Now don't try and make that just one straight line because this did not look like one straight line. So here is our graph of the inverse function. And we said that the graph of the inverse function should look like a reflection of the original one about the line y equals x. The line y equals x goes to the point 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, because the y and the x value are literally the same. -5, -5. You better know how to graph lines in this course. No exceptions. So it's kind of, you might be able to see it with them on separate graphs, but let's actually put them on the same graph for a demonstration, and then we'll be done with the section. So let's put both the function and its inverse on the same graph. I'll also graph the mirror, that line y equals x, and I think we'll be able to see it. So in red, I will do the original function. Let me go ahead and label my axes and numbers. Let's go, we gotta go right. 1, 2, 3, 4. I'm gonna try and keep these symmetric. 1, 2, 3, 4. And then down 1, that looks a little too far. 1, 2, -3, and then left 1, 2, -3. So in red, the regular function, -3 comma -2 was right here. -1 comma 0 was right here. 4 comma 2 was right here. Connect. This would have been a piecewise function, by the way. Everything look okay? Yes. So there's our regular function. Now let's do the inverse function. That was -2 comma -3, so left 2, down 3. Then 0, -1, and then 2 comma 4. Connect. And it almost looks like I'm drawing a chromosome. That's actually a good sign. That's our f inverse of x for this particular problem. And then here's the line y equals x. It just goes to the points 1 comma 1, 2 comma 2, 3 comma 3. It goes to the origin 1 comma 1, 2 comma 2, 3 comma 3, however many points you need. Oops, that was awful. Just make this a little bigger. All right. And there is the line y equals x, which is our mirror. And I think that looks like a pretty good mirror, even with my lack of artistic ability and blind drawing tablet. Flying blind. Inverse functions is an excruciatingly important concept in the world of calculus. I'm not going to get into all the details of why and when you'll see it and whatnot, but just know that dealing with inverse functions is not going to go away. The inverse functions are basically Jeopardy. We have the answer and wonder what the question was. And the inverse problem in math can be a very complex one, because sometimes if you have an answer, there could be multiple questions where that answer is valid. You might have an answer and it seems like there's no question that works and you have to like reimagine things. Blah, 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 blah. All right. 2.8. In our last 20 minutes, 25 minutes, we've got distance, midpoint, and circle formulas. 3 formulas that you have to memorize. Memorize the formulas I'm about to get you. These should be subnotations, so that's x little 1, comma y little 1, just like with slope. X little 2, comma y little 2. Again, just like with slope. So the distance between any 2 points is found by the formula. D equals big ol' square root, big square root. Then a parentheses. x2 minus x1 squared plus y2 minus y1 squared in parentheses. Memorize that, memorize that, memorize that. There is no formula sheets in a pre-calculus course, not pre-calc 1. The nice thing is this formula is kind of an algebraic rearrangement of the third one I'm going to give you, and I'm going to rationalize as to why that is, but not yet. We're just going to take this as the gospel for now. The nice thing is there's a lot of things you can get wrong with this formula and still get the right answer. Because you have a difference being squared, let's say your x2 was 5 and the x1 was 1. 5 minus 1 is 4, 4 squared is 16. Let's say you did 1 minus 2 instead. 1 minus 5 is -4, but -4 squared is positive 16. You get the same answer. So in fact, the order of the 2's and the 1's in both of these is arbitrary. Now remember I said with the slope formula, the order was arbitrary as long as you were consistent. Here, you don't even have to be consistent. You can do x2 minus x1 and y1 minus y2, and you won't even screw up. It's convenient. Also, the order, I accidentally hit save, didn't I? Yep. And it's chugging, there we go. The order that you write these parentheses is interchangeable. because this is just going to be some number like 16. This is going to be some number like 25. 16 plus 25 is the same as 25 plus 16. There are tons of things you can get wrong and still get the right answer. Now, what you can't do is you can't put a y value here and an x value here. That would definitely give you a bad answer. All right, so for example 1, find the distance between, and for A, we're going to have 2 comma negative 5 and negative 3 comma 6. Now this is a square root problem, so you have to remember all of those different simplifications for square roots. If you have something like the square root of 8, you'd have to write the 8 as 4 times 2, pop that square root of 4 out, you'd get 2 square root of 2, something we discussed as prerequisite material. Go back to that section and practice the prereq regarding that concept if you have to. All right, so if you want to label these, the 2 would be your x1, the negative 5 would be your y1, or I could call both of those 2's, it wouldn't really matter. This would be your x2 and your y2. So your distance formula would be the square root, big old square root of, I'm going to go in the order I see just for consistency, but again, no, there are a lot of different orders you can write these things and still get the right answer. x2 minus x1 is negative 3 minus 2. Watch your signs, squared. And a plus. Be careful. The insides are minuses. The thing between them is a plus. A lot of people accidentally make that a minus here. That's not. And then y2 minus y1, that's 6 minus, be careful, negative 5. Double negative scenario there. So that distance is big old square root of. Negative 3 minus 2 is negative 5. Then squared. Plus, I'm going to skip the rewrite here. That's 6 plus 5. I'll say it. 6 plus 5, and 6 plus 5 is 11. I don't need a parenthesis since it's positive. That's the square root of negative 5 squared is 25. 11 squared is 121, and yes, that's positive 25. If you forget your parentheses, you might make a mistake there. And then 25 plus 21 is 46. That's the square root of 146. In the interest of time, I will tell you there is no way to break that one up. You don't know the square root of 146, and there's no way to factorize that number and have a square root of one of the factors. A nice trick is try dividing these numbers by numbers you know a square root of, like 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169. That's how you can really quickly tell if you can simplify a square root. B, let's go with points of 0, 4, and negative 1, negative 2. And if you wish to label them, that's x1, y1, x2, y2. So the distance here, big ol' square root, memorize that formula, parentheses, subtracted, and this will be the x's, negative 1 minus 0, the x2 minus the x1. Then a plus here, and the difference is the y's being squared. And again, I could go 4 minus negative 2, and I would conveniently get the right answer, but I'm going to be consistent in the order negative 2 minus 4, y2 minus y1. No double negatives the way I've done it this way as well, so that's kind of nice. So D equals square root. Now, the problem is don't get a bad habit. Don't start rearranging things here and think you can do that with slope because, again, you have to be consistent with slope at least. If you do 1 minus 2 in the top, you got to do 1 minus 2 in the bottom. Negative 1 minus 0 is negative 1, so that's negative 1 squared, plus negative 2 minus 4 is negative 6. That's negative 6 squared, which is the square root of 1 plus 36, which is the square root of 37, which again, in the interest of time, I'll just tell you, cannot be simplified. 37 is prime, in fact, so definitely can't simplify it. We're going the distance. Next up, we're about halfway through it. Ha ha ha, halfway midpoint. Mid means half. Mid means half. Midpoint is halfway between 2 points. Again, subnotation here, x1, y1, and x2, y2. And that midpoint formula is found by this thing that you'll have to memorize. And I'm just going to tell you, I don't memorize the formula. I memorize this as a concept. A midpoint is the halfway point. Halfway between 2 points would be their average. So we're literally just going to average the coordinates. What's an average mean? You add them and divide by however many there are, which there's 2 coordinates. Now it's a midpoint, so it's a point. This is going to be some x and y value. So each of these has their own little formula, but they're the same idea. We're averaging things. We add up a bunch of things and divide by the number of things. So it's going to be adding and dividing. So this is an x coordinate, so we average the x values, which is x1 plus x2. There are 2 of them, so guess what? We divide by 2. Same exact thing for the y's. We're averaging the y's, so we add them. There's 2 of them, so we divide by 2. Again, I've never seen any reason to really say memorize that as a formula. I prefer logic and understanding and reasoning, and understanding that midpoint means average the x values, average the y values, because the average would be the halfway of 2 points. Now, this only works for 2 points. 3, 4, 5, 6, 7 points, that's a whole different concept. We're not doing that though. Example 2. Guess what we're doing? I'm sure you guessed it. Find the midpoint. Much easier to do, generally speaking. 2 comma negative 5. That'll be the first point. Negative 3 comma negative 6 will be our second point. So this is literally the exact same as 1a. In 1a, we found the distance between them. In 2a, we're going to find the halfway point between them. You need labels. x1, y1, x2, y2. So your midpoint, you were just averaging the coordinates. So average the x values, 2 plus negative 3, not minus negative 3, all over 2. That distance formula had pluses and minuses. This midpoint is just averaging, which means adding. Then average the y values, negative 5 plus negative 6, over 2. So that midpoint, 2 plus negative 3 is negative 1, so that's negative 1/2, comma. Negative 5 plus negative 6 is negative 11, over 2. Something's wrong. What did I do wrong here? That was supposed to be a positive 6. Not a big deal. I'm just going to use red to show you what I'm changing here. That was supposed to be a positive 6, so that it was the same as the original, and that's my bad. So that means this was supposed to be a negative 5 plus 6. Negative 5 plus 6 is positive 1. Sorry for that mistake, but I caught it. It wouldn't have been an issue. It just wouldn't have been the same as example 1a. I would have been a slight liar there. I didn't do any math wrong when I had y2 labeled as negative 6. The math was correct. I just didn't mean for it to be a negative 6. So here's what's cool about distance and midpoint. If you were to plot these 2 points, if you went and plotted 2 comma negative 5, which will be somewhere down here, and then negative 3 comma 6, which is somewhere up here, the distance between those 2 points would be the square root of 146. That's the length of that line. And then this halfway point, negative 1/2 comma 1/2, is about here. That's your midpoint. And that coordinate would be negative 1/2 comma 1/2. So sometimes we're interested in taking a segment of a line. Maybe we just need to know its distance. Maybe we need to know a halfway point. Halfway points are great for finding balances of things if you're doing physics problems. All right. B, negative 5 comma 12, we're doing a different one, and 7 comma 20. So our midpoint. Average the x values, average the y values. Your x1 is the negative 5, the y1 is the 12, x2 is the 7, y2 is the 20. So add the x's and divide by 2. Add the y's and divide by 2. Negative 5 plus 7, and then 12 plus 20. So our midpoint, negative 5 plus 7 is positive 2 over 2, comma. 12 plus 20 is 32, then over the 2. Reduce your fractions, you get 1 comma 16. And that would be our midpoint. Ten minutes. Circles. Guess what I'm about to do? I'm about to give you a formula that you will have to memorize and understand how to apply. Now this one, this is kind of a two-way street. Sometimes I'll say the center of the circle is here and this is its radius, and I'll ask you to write the equation. But I might also give you the equation instead and ask you to identify the center and the radius. So it works either way. So the equation of a circle, write this out. A circle centered at h comma k with radius r as the equation. Why are we using h comma k? Because that's just what classic mathematicians do. And this h and k are going to be seen in what we call vertices, or a vertex for singular. This h and k will be seen over and over and over eventually. All right, so we go parentheses, x minus h, then squared, plus parentheses, y minus k, and then squared, and then equals r squared. This formula right here is just a rearrangement of the distance formula. They are extremely related to each other in the same way that the slope formula was related to the point slope form of a line. You just change the 2's and 1's. You change the 2's, you just drop them, so that's an x and a y. And the x1 and the y1, you just instead call them h and k for reasons. You could still call them x1 and y1 instead of h and k. There's nothing wrong with that. It's just a choice that classical mathematicians have made. H and k we like to use for vertex points, for centers, etc. So if you took the square root of both sides, this r would be the d, so the distance from the center to the end of the circle. And again, this is like your x, whoops. This is like your x2 and your y2. This h is like your x1, the k is like your y1, and the r is like your d. If you just take the square root of both sides, boom, you have the distance equation. So me, I don't memorize both. I memorize one and then do that little logic and reasoning to get the other. I don't like blatant memorization of things. I'm not very good at it, honestly. I'm a lot better with reasoning. Why is this thing that way? And the idea is because the formula for a circle is literally just measuring the distance from the center to the end. And that's always the exact same. It's a radius. All right, so let's try these out. And I have 3a typed up for some reason, but not b. Sometimes I do weird things like that. We're going to write the equation of a circle given that the radius is 4 inches and the center is at the origin. The origin meaning 0, 0. So 0, 0 is our h, k. X, y, h, k, they go in order. So that says the radius is 4, and we're just going to plug those 3 numbers into the formula we have above. That's all we do. You do not plug anything into x, you do not plug anything into y. You leave them as x and y. So it goes parentheses x minus something, and then you'll square it, and a plus, a parentheses with a y minus something and squaring it, and then equals whatever your radius is, but squared. Just cookie cutter. All right, well, what was the h? That was the 0. What was the y? That was also 0. What was the radius? It was 4. The right side is not just 4, it's 4 squared, which you do need to simplify the sum. Well, anything minus 0 is itself, so that's just x squared, plus same thing, so that's just y squared equals, and 4 squared equals 16. That is the equation of a circle with a radius of 4. I didn't actually ask you to draw it, but if you did, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I just like to put points 4 left, right, up, and down from the center, which the center was at the origin this time, and then try and draw your best circle around that. My math lab makes this entirely too easy. It draws the circle for you. You just have to point out where the center is and what the radius is. And I think you can use your mouse to drag out the radius. But remember, If I do something by hand, you're expected to be able to replicate it by hand as well. I don't have to give my math lab tests. I'm not always going to, maybe. All right, B. This will be our last example. Admittedly, we will do one more example next time, next class. But I'm still saying the test is 1 week from today since it's only one single example. R equals the square root of 7, and I'm just going to say the center centered at 2, -5. There we go. Oh, radius is a square root. That sounds awful, doesn't it? Nope, don't let it terrify you. So the radius is the square root of 7. If the center is 2, -5, that makes the 2 the h and the -5 the k. Again, if you just really don't like that, you can call it x1 and y1, and the formula goes x minus x1 and y minus y1. It's more like the equation of a line and point slope form then. You do however you need to do, as long as you can understand if I use a different letter than what you'd use. So cookie cutter, it's x minus something squared plus y minus something squared equals the radius being squared. The x goes with the x coordinate of 2. The y goes with the y coordinate of -5, but since there's a double negative, you got to do this. And the radius was a square root of 7, so we have that being squared. Which the cool thing is, square roots and squares cancel, so the right side is just 7. And then x minus 2 being squared plus, let's change that to y plus 5 being squared. And that's our answer. You might say, Mr. Beckner, why aren't you doing the x minus 2 times x minus 2 in foiling and the y plus 5 times the y plus 5 in foiling? Sure, you could. It's going to look a lot uglier. It's going to end up looking like, oh boy, x squared minus 4x plus 4 plus y squared plus 10x plus 25 equals 7. And you could change that up to be x squared minus 4x plus y squared plus 10x plus 29 equals 7. You could even move the constant over. But when you look at this red version, even though they are still equations of circles, they're just algebraically different looking, I can't identify anything. When I look at this, I can look at this thing right here, and I can tell you the radius and the center in the snap of a finger. I can't do that here. So it's not beneficial to expand anything in that way. It doesn't help you. Now, if this was a slightly more advanced pre-calculus class, what we do there is we'll give you these red versions and ask you to turn them into the black versions by completing the square on the x's and the y's, but it works mechanically a little bit differently than when we were completing the square back in chapter 1. You still have to do that halving and squaring of a number, and then you add it to both sides, but you're going to be doing it for the x's and for the y's. That's the mechanical difference. So again, that's not something we're going to cover in the TCC version of Pre-Calc 1. I wish we did, but we don't. It's not in the homework, so I'm not going to test them. All right, so in the last 2 minutes I have, next class I'm just going to point out there will be an example for A and B, and that's exactly what we're going to do. We're going to start here, and we're going to learn how to identify the center and the radius. It's not a complicated process, though. But because that's the only example we have left, I'm going to say we are good enough to say we are.
All right, before I show those dates again, I just want to point out, I said this in chat, but this right here, I wrote an X, I said an X because I was rushing. These are supposed to be Y's. So again, this should say Y squared plus 10Y plus 25. And then this would be Y squared plus 10Y plus 29. So again, make sure that if you were going that far, that you make those 10 Ys, not 10 X's. Sorry about that. And then just gonna pull up our due dates. So 2.5, 2.6, 2.7. Again, we've basically finished 2.8. I would advise that you go ahead and start working on that homework, even though I'm going to make the due date for it a week from next class. So we have our 3 homeworks coming up. We know when our test is going to be. We know that our review will be available soon. I'm going to go ahead and make that available sooner than later today, just FYI, so you should see that available very soon. And we will see you next class. As always, email me if you have any questions. Take care and have a good day.